Hello. You are now hopefully starting to feel comfortable with the first and second laws of thermodynamics. In fact, I hope when I put these two results up on this slide that these feel familiar enough for you to consider them old friends. I want to express these ideas in words. The first law, remember, tells us that the internal energy of an isolated system is constant. Alternatively, the change in the internal energy of a system is equal to the work done on the system plus the heat input into the system. In this expression, the little horizontal bars running through the d's of the dw and dq indicate the fact that the work, W, and the heat, Q, are not functions of state. In other words, dq and dw are not exact differentials, and thus the heat input into the system, Q, or the work done on the system, W, will depend on the path taken in making the transition between states. For the internal energy, the same result does not hold. Internal energy is a function of state, and the change in internal energy that occurs on moving from state A to state B does not depend on the path taken between the two states. We can thus safely use a normal D when writing the differential of this quantity. The second law tells us that the entropy of an isolated system increases during all spontaneous transitions. To be clear, here, entropy is still a function of state. So if I move from state A to state B, the change in entropy will be the same regardless of the path taken. In an isolated system, what the second law tells us is that if state B is lower in entropy than in state A, then this transition will never take place via any path. We arrived at the second law of thermodynamics by examining the behavior of the Carnot engine. The start point to these considerations was our realization that heat always flows from hot things to cold things. In other words, if I place something hot next to something cold, then the temperature of the cold thing increases and the temperature of the hot thing decreases. Furthermore, I have now explained a number of times that this happens because entropy is transferred from the hot thing to the cold thing. In this video, we are going to do something that might at first sight appear contradictory. We are going to prove that this behavior, the hot thing getting colder and the cold thing getting hotter when they are placed in contact, is consistent with the first and second laws of thermodynamics. If you are confused about why we are doing this, then this is fine. The logic here is circular, but you must remember that the laws of thermodynamics are axioms. They are unprovable statements about the universe that have been designed by scientists to be consistent with the behaviors of the universe that we have observed thus far. In other words, we can prove many of the things we observe if we assume that the first and second laws of thermodynamics hold. As an example, and as we are about to show, we can prove that the laws of thermodynamics are consistent with our observation that when hot things are placed next to cold things, the hot things get colder and the cold things get hotter. Depending on your philosophical bent, the laws of thermodynamics are thus either two profound statements about the true nature of reality, or a useful mnemonic device that help us to remember the results that we observed in the experiments we have performed on the universe thus far. This is a philosophical discussion for another time, however. Let's move on and prove this result. To do this, we are going to define the constant volume heat capacity as the partial derivative of the internal energy with respect to temperature at constant volume, obviously. The heat capacity is an example of a thermodynamic quantity known as a response function. If we integrate both sides of this definition, but do not write integral signs out of sheer laziness, we can write the following. Notice the equality here only holds if we hold the volume of the system fixed. If the volume is not held fixed, then the expression does not hold. We next remember that we can express the infinitesimal dE on the left-hand side of this expression by combining the first and second laws of thermodynamics. We thus have another old friend, dE equals TdS minus PdV. The volume here is held fixed though, so we thus have dE equals TdS, which we can equate with dE equals CV dt. Furthermore, this expression is always true as long as we hold the volume of the system fixed. If we now rearrange this expression, we get to the following. Cv over T is equal to the partial derivative of the entropy with respect to the temperature at constant volume, which is a result that will come in useful later on in this video. Let's leave this for a moment though, safe in the knowledge that we will come back to it later, and move on to something slightly different. In one of my previous videos, I demonstrated that the internal energy is minimized when the system is at equilibrium, and that the entropy is maximized. I mention this now because a similar result holds for all the thermodynamic potentials. If we consider the Gibbs free energy G, for example, which we have remembered is equal to the enthalpy H, subtract the temperature T multiplied by the entropy S, this quantity will be minimized at equilibrium, because H will be minimized because it contains the internal energy, which we know to be minimized, and because we subtract from this the temperature multiplied by the entropy. We know that the second of these terms, the entropy, is maximized and thus that minus S will be minimized. With this realization that the Gibbs free energy is minimized at equilibrium, we can come to a second realization. Any small fluctuation away from equilibrium will tend to increase G. Given this realization, we can write the following inequality. At heart, this expression is telling us that if the state of the system, the values of the extensive variables, change by a small amount, that is to say, if the entropy changes by an amount delta S, the volume changes by an amount delta V, and the internal energy, also an extensive thermodynamic variable, remember, changes by an amount delta E, then the Gibbs free energy will increase. Notice that in writing this expression, we have exploited the properties of reservoirs that were discussed in the video where I have introduced the thermodynamic potentials. In particular, I have used the fact that the reservoir is so large that the values of the intensive quantities are unaffected if the system exchanges entropy, energy, or volume with its surroundings. We can rewrite this inequality as shown at the bottom of the slide. What is more, we can take this business further by recognizing that we can use the Taylor expansion to write the delta E on the left-hand side of this inequality in a different form, as shown here. Furthermore, we learned in the videos on the internal energy that the partial derivative of the internal energy with respect to entropy at constant volume is equal to the temperature. Furthermore, the partial derivative of the internal energy with respect to volume at constant entropy is equal to minus the pressure. If we now substitute the result shown here into the left-hand side of the inequality at the top of this slide, although this is not shown explicitly, it should be easy enough for you to see that we have a T delta S and a minus P delta V on both sides of the equation. These terms obviously can be cancelled, and we are thus left with the following inequality. We can simplify this further by realizing that delta S and delta V are always real numbers. As such, delta S squared and delta V squared will always be positive. Hence, in order for the inequality to hold, the coefficients of these two terms must both be positive. We now need to remember a few things. The first of these things should by now hopefully be familiar. Temperature is the partial derivative of the internal energy with respect to the entropy at constant volume. Notice that if we differentiate the right-hand side of this expression with respect to entropy, we get the second derivative shown at the top left of this slide. Remembering that equality is maintained as long as we do the same things to the left-hand side and right-hand sides of an equation, we can thus rewrite this second partial derivative of the internal energy as a first partial derivative of a temperature with respect to the entropy at constant volume. Now remember from earlier in this video that I showed that the constant volume heat capacity was equal to temperature multiplied by the partial derivative of the entropy with respect to temperature. This result is important because it allows me to rewrite the partial derivative in my inequality here as T divided by CV. We arrive at a final important result once we realize that, except in some extremely special cases, temperature is positive. Hence, for T divided by CV to be positive, we must have CV greater than 0. In other words, when you heat something up at constant volume, its internal energy must increase. In addition, if you heat something up at constant volume, its entropy will increase. As discussed earlier in this video, the heat capacity is an example of a response function. There are a number of different response functions, and we can use the same logic shown here for the heat capacity to demonstrate that these quantities must also be positive. In order to cement what we have done then, let's apply this logic to a second different response function. This time we are going to look at the constant entropy compressibility, which is given the symbol kappa underscore s. We will initially define this quantity as 1 over PV multiplied by the partial derivative of the internal energy with respect to the volume calculated at constant entropy. If we once again exploit the fundamental theorem of calculus and rewrite this as the lazy man's integrals, i.e. if we write this with an integral, if we write this as an integral without integral signs, we arrive at the following expression, which only holds if the entropy is held fixed during the transition. We next recall that dE is equal to TdS minus PdV, and that we are at constant entropy, and that ds is thus equal to 0. If we now set the right-hand side of the equation at the centre of this slide equal to the right-hand side of the equation in the top left of this slide, which we can do because the left-hand sides of these two equations are both equal to dE, we thus arrive at minus PdV equals kappa S PV dP, which we can rearrange as shown here. This is a much more usual definition of the compressibility. We have here that the compressibility of a material is related to the partial derivative of the volume with respect to the pressure, which makes a lot of sense given the name of this quantity. We compress something by pressing down upon it, i.e. by applying a force or putting the thing under pressure. Let's now turn to the stability condition in this case. Remember that we have derived the two inequalities shown at the top of this slide. Once again, remember that we can relate the pressure, an intensive quantity, to a partial derivative of the internal energy with respect to volume. Differentiating the right-hand side of this equality with respect to volume gives us the second partial derivative shown in the equality at the top right of the slide. We could thus rewrite this inequality in terms of the partial derivative of pressure with respect to volume. Much as with the heat capacity case, we now recall the definition of the constant entropy compressibility and find that the partial derivative in our inequality can be written in terms of the response function. Substituting this into our equation, we thus find that the compressibility must be greater than 0. In other words, we have proven, starting from the statements of the first and second laws of thermodynamics, that when pressure is placed on an object, its volume decreases, which is in accordance with our everyday experience. To conclude then, I will finish by showing the first and second laws of thermodynamics once more. In this video, I have shown how we can demonstrate that the mathematical results that we can derive starting from these two axioms can be used to rationalize all of the phenomena we observe in experiments. In other words, the mathematics that we have developed based on these two axioms is consistent with the reality of the universe as we perceive it. Thank you for your attention.